So welcome to this lecture on advanced digital design, digital system design in the course digital system design with PLDs and FPGAs. In the last lecture we have seen how to kind of decide the minimum frequency of a state machine and with regard to the data path, and also we have looked at the conditions. The inputs are not very neat waveforms, and when there are the real life inputs are there, how to handle it because it may not meet some kind of requirements we put forth. And we also have started looking at the features, what is the difference between Millet and Moore kind of outputs, and maybe how to at least in some cases how to make what is a Moore output into a Millet output, or at least to illustrate that is what we have done. We have converted a Moore output to Millet output, and I have seen what are the advantages, what are the disadvantages. We have not completed it and we will complete it and today. So let us look at the last lecture slides, and we have looked at the minimum frequency, and we said the main game is, suppose if you look at 3 inputs and put this clock, then we soon find that this clock is not able to detect change in this input 3. So it is like we need at least one clock edge, active clock edge during that change in 3, and to kind of an ideal example we have taken some square wave, and it is soon clear that at least one clock period less should come within this kind of change, and change being symmetric or regular, we can say that the clock frequency should be at least twice that of the maximum input frequency. That's a kind of thing we have told, and that is not surprising because a state machine is basically sampling the input, looking at the inputs for any change, any event, and trying to respond it with output, a sequence of output sometime. That's why it's called sequential circuit. And input, in real life input is not a square wave or periodic waveform, but the pulse width should not be the criteria, and that means that you have an input which changes for a while, it becomes 1 for a while, say a few nanoseconds, then say 1 microsecond it is inactive, again it comes like for this change to be detected in a kind of very straightforward way, then one would expect to have a clock period kind of matching this pulse width. But we know that we talked about the frequency, and we know that the frequency is quite low. So definitely this pulse width is not the criteria for choosing the minimum clock frequency of the state machine or the controller. Also the kind of waveform suggests that there should be some way to stretch the waveform, and then suppose in this case if you stretch it here, you could definitely use a lower clock frequency for the state machine. And we have seen some practical example of how to stretch it. But before that I said something much more important. Here the requirement is only to detect the event, detect that it is input has changed the state, okay, and respond to it. But maybe in some cases you have a kind of accuracy requirement. That means that there is a timing pulse, and say we are trying to detect, say it has gone high in response to some event, the state machine has made it high or enabled something to something which has made the signal to go high, and is waiting for it to go low, which needs some precise timing. And in that case if you use a clock like this, it will detect that it has gone high here and it will detect that it has gone low. Perfectly okay if just we are trying to recognize that it's gone high and gone low, but if you need some precise timing to be kind of measured, then you know that this clock is much better, because this clock detects that it has gone low after such a long time, but this is much faster. So that means, suppose if somebody says there is a plus or minus error, okay, within which need to be detected, or within which an event has happened, within which that has to be responded or whatever, then like this is the event and it should be detected with an accuracy of some kind of time period, then you know that the clock period should match that error, okay, then only we can detect it. That is what I mean by this, you know. And this situation arises, you know, you have an event and somebody say the controller has to kind of respond to it within a certain time, okay. It is nothing to do with the pulse width, maybe the pulse itself remain high for a long time, it is a very rare event, but the requirement is that the event has happened, but this next event may happen after 1 second, but somebody say that the response should be as fast as say kind of 1 nanosecond, then definitely you need to detect it with that accuracy, you need that clock period to be 1 nanosecond, otherwise there is no way to do that, okay. So that is what I mean. And now let us come back to this kind of clock stretching, and we have seen one kind of circuit but which not very much used, I have just shown something to illustrate. So this is the pulse catching circuit where the clock is, this is the kind of pulse we are trying to extend it, that is a clock and the input is 1. What we do is that we use a 2-stage shift register, so that we are not sure, because this clock and this pulse is not synchronized, so we are not sure when this will happen, and that is double clock, so that at least you get one period width here, the synchronized pulse, this one. So in the picture it is shown as almost 2 clock period, but you know that this has gone up, this edge could have been very near to it, and then you get only 1 clock period, and that is shifted and it is reset, okay. So basically it is stretched, and if you put a multiple stages of flip flops, you can stretch it any longer, but then it depends on the clock of the FSM, but if you use a lower clock there is no reason to kind of stretch it, you know, more than 2 stages, because we have 1 clock edge, you know, coming in that period, that is all what we require kind of to be detected by the state machine. So there is no reason to put more flip flops, because after all this clock is the clock of the state machine, so 2 stages should be enough. I have shown a practical circuit which is not stretching it. What we do is that we as output, when a pulse comes, the output goes high and stay there till the next pulse come. When the next pulse comes, it goes low and it goes to the state machine, and what state machine does is that every edge, every positive and negative edge, you can make kind of a pulse, and that is a pulse to level converter. This is the circuit you have, the pulse clocking the flip flop, and you have a kind of toggle flip flop. The Q is fed back to D through an inverter. So first pulse come, it is high, next pulse come, it is low, and our aim is to get a pulse here at the receiving end and 1 pulse here, okay. So we do a synchronization for timing reason to avoid the metastability in flip flop. We have not discussed that, but at least for the time being you just try to put a double stage synchronizer, which is nothing but same clock and you two flip flops in series. And here is what we do, you do an I2, the input of the flip flop and output of the flip flop you combine, and if you do I2 I3 bar, you get a pulse here, the opposite I3 I2 bar, then you get a pulse at the negative edge, and we want pulse at both edges, because maybe in the last class I did not kind of stress it, because here there is 1 pulse, then it goes high, when next pulse come it goes low. So at the receiving end we need a pulse here and a pulse there, depending on which is of the width of the the state machine clock, and that is what we have done. This is the clock of the state machine, and you do I2 I3 bar, you get a pulse at the positive edge, I2 bar I3 you get the negative edge, you OR it, then that becomes I2 XOR I3. So this is an XOR gate, then you get pulse here and pulse here, and you know that it comes with a delay of the clock period, and that perfectly works fine for the state machine because this is high during the active edge of the clock, and this is correctly detected by the state machine. So this is a very practical circuit, very much used, though there are some kind of timing constraints probably which at this stage we will ignore. It is not that it works for all cases. There are some restriction on because of this double stage synchronizer, because you know that for the I2 to come here it takes 2 clock period, okay, and so that means between these 2 pulses there should be at least 2 clock period gap of the state machine, okay, nothing to do with the pulse itself, okay. After the pulse comes here, you know that it passed through 2 stages of flip flop, and that introduced a latency maximum of 2 clock period, because this is not the input pulse is not synchronized to the clock. So it may take maximum 2 clock cycles. So it is important that the gap between these 2 pulses is at least 2 clock period of the state machine clock, or the receiving domain clock we can say. So that's a circuit, and that I have shown it combined together. You have a kind of pulse to level circuit or pulse to toggle circuit, and this is a toggle to kind of pulse back circuit. And we have discussed when we have a register to register path, be it a state machine or a sequential circuit or a data path, where a register, a combination circuit register, in the case of the state machine or counter this could be next state logic, in the case of data path this is some computation, but the clock period is chosen as TCO, TCOM and T setup all maximum, and T clock period should be greater than that. And to avoid hold time violation, this delay plus this delay which is minimum delay should be kind of greater than the minimum hold time. And very many a times the people ask a naive question, why this cannot be the clock bar. As I said, there is no great issue with the trouble is that you are looking at a part of the whole, and if you have an whole picture put in mind, then you will soon realize that this is not possible, because this is clock bar, and again next is clock, that is fine, but then there is a feedback from back here, then you find this is the last one was clock and the feedback is also back to the clock, not to the clock bar. Similarly you have a path here and it terminates at clock bar, and you have another path here which terminates at clock, then both output go to another register, then you are confused whether that should be either clock or clock bar, but cannot be both, then you are stuck, okay. Similarly, like you have a data path giving the signal to the state machine, and maybe state machine receive output in response to a positive edge triggered clock register and a negative edge triggered register. So there is a big issue. So you have to stick to one polarity, it can be clock or clock bar, and timing wise, and we have seen there is no big deal, because if you use if it is possible to use half the clock period, then this T clock min by 2 has to accommodate the maximum delay. The only thing is that the clock period will be twice that of the clocking by single edge. So the clock frequency comes down, that is only kind of advantage, but practically it is not possible to do that. That is a simple answer, and this is where we have looked at, and we were trying to kind of understand the difference between Moore and Milley output, because in most textbook would deal with very simple cases of state machine with one input and one output, and somehow many a times it appears that at the beginning you can kind of decide the state machine is Millet or Moore, and accordingly you, at least that is a kind of it may not be intended by the textbook, but that's the kind of picture many a times students get. But in practical cases there are, as I said, there are maybe so many states, maybe more than 20 states, more than 15 outputs, and some are Moore, some are Millet, and one it's not a kind of ideological or some matter of taste to choose Millet and Moore output. It's not that you like Millet or something like that. It is there are some cases where Millet is the most appropriate thing, and some cases it cannot be done at all. So you have to kind of choose, and that is what we are trying to do this. And this is an example which is drawn from our case study. That's why I take the case study, so that you can illustrate the various kind of concept based on that once you understand that. So this is our ADC kind of data acquisition controller. So there when we discussed, we said that at the power on it comes to the state 0, and when the start it is waiting for the start from the host processor, and when start is low remain there, and we are only looking at this particular output which is of kind of concern, and the start of conversion pulse is 0, and when the start comes it transits to next state, and there the start of conversion is made 1, and there is no condition on that state. Next clock it transits to the next state and SOC is made 0. So this state remains there for 1 clock period. So you get a pulse of which 1 clock period and you make it 1. Okay. Now let us think whether we can make this as this is definitely a Moore output, because this is a decode of state 0, this is a decode of state 1 and so on. So if the SOC is 1, we know that in the state diagram SOC is 1 only in one state, so it is decoded as we know that this is 0 0, this is 0 1. So it is decoded as Q1 bar and Q0. Okay, that's all. That's the equation, that's a decode of the present state. So what we are trying to do is that we know that already that this SOC has something to do with the start. Okay, when as long as the start is low, SOC is low. When the start goes high, the SOC becomes 1. So why not kind of envisage a Millet output in that way. Okay, that means that like this, the machine is in state 0 at the power on, it is waiting for the start signal. So as long as start is not active, remain in this state, and we say instead of saying SOC 0, we say SOC is 1 if start is 1 in this state, we are not transiting to another state. Okay. So we are hoping that sometime being in this state the start becomes 1. So that state, that means Q1 bar and Q0 bar, that is 0 0, and start is the decoding of SOC, it is a Millet output, and also upon the start it transits to next clock edge, it transits to the next state, and we are skipping S1 because that is done here. So we skip to S2 where the SOC is 0. So that is the Millet output, that is why it is converted. So I think you get the picture, and I said already you see an advantage, there is one state less, and you can imagine in a huge kind of state machine where there is lot of kind of outputs which can be made Millet output, then you get the states less, so number of flip flops could go less, and if the number of flip flops are less, maybe the next state logic, because it is a function of the present state and input, the area of that could become less, and the output logic, which is a decode of the present state and input, that becomes less, and so on. Okay. So the area can become small, the state machine can be clocked very high, high frequency, it occupies less area, reduces the power dissipation and so on. So many advantages one can think of, and as I said that for a clever student like as an advantage, there already should some indication of a disadvantage, there is a timing issue because you are remaining in this state, and when the input goes high the output is high. Okay, that already should give you a kind of hint as to what can go wrong. So let us kind of illustrate it much more than that. This is not a quiz, so I want that concept to be ingrained in your mind so that you design something. I don't know what you are going to design. Maybe you design something trivial, then it doesn't matter, like if you design a computer game where there is a chip, and if something misfires, it's not a great deal. But if you are sending a rocket to the space, and if a slight mistake could put things in a jeopardy, so maybe you are part of an aircraft which is being designed, and there is a controller which you are designing as part of something guidance, then it has to be precise. So let us kind of imagine the worst scenario, the critical application, and handle this. So let us look at the timing diagram of this kind of two outputs. So this is a scenario. So we have a very simple 3 state and 2 state. So we have the clock, and we have a start signal which is going high like that, it goes high after the positive clock edge, and for the 2 clock period say it is there. So now you look at the Moore machine, okay, so or Moore output. So there you see that at the beginning start is low, so definitely you know that this is S0. Here also you know that when the clock edge comes it is still low, so this is S0, and the next is S0 because there is no transition. When the clock edge comes it is low, so it is S0. But here you see when this clock edge comes the start is 1, so the next one is S1, and you know that S1 in the next clock edge without any condition transit to S2. So if you look at the Moore output, the states are S0, then S0, S1 and S2. Okay. Now how does the SOC output looks like? We know that SOC is 1 when the state is in S1. Okay. So the output will come like this, you have SOC is decoded from the present state, and it will be like that. It will not match the period because there is a output logic delay, because output is decoded from the present state. So there is a TCQ delay of the flip flop plus the T output logic, that is it, this one. So this is TCQ, maximum TCQ plus maximum output logic, that is the worst case gap you can have, and it appears like this. Okay. Now let us look at the melee kind of output. We know that there the same thing, the state is S0, the clock edge comes it is still 0, it is S0, and it start has gone 1, and the clock edge, and it goes to S2. There is no S1 in the melee output, so you remember that, there it was start is high, it comes to S1 then S2, but here start is high, it just goes to S2, but it generates in S0 an output. Okay, SOC is generated as a function of start. So that is what we are going to see. So here in the melee case the first one is S0, second one is S0, the third one is S2, but our output, now you look, output is in state S0 and the start is 1. So basically it is a decode of that, and so you kind of AND both together, this is 1 and this is 1, and since start is going high here it will come with a delay because of the decoding delay. So you have something like that, you can imagine little more delay because start is going. So I have not shown that, but this is delayed a bit. So this comes like that, it is very nice. So if you look at the advantage, yes, one state less, okay, good, and the output appears kind of much before, at least a clock period before. The Moore output looks good, it responds faster. Okay. Now the game comes, the question comes, what is wrong with this? Here probably nothing can go wrong, but here you see the output is a function of the state and the input, and this input, mind you, has got nothing to do with the clock, and this input is not synchronous with the clock because this input is our state machine clock, and this comes from a host processor, and that processor has another clock. So this may be generated in relation to that clock, which could be much higher than this. So this pause can appear anywhere, and the question is what happens if the start come late like that. I have shown with a fainted kind of mark. So if it is, suppose the start is coming very close to this positive edge, then what happens is that the SOC become a kind of glitch. We said that there is no great timing restriction on SOC in the sense that can be a narrow pass, but if it is very narrow it may not be detected, or this could be thought of as some other output, not SOC. So since the input, if there is a case where the input is not synchronized and at the output you will get a glitch which may not happen in the case of Moore kind of output. So it's a bad news, okay. It means that it's a bad news as well as a good news. It depends on the way you look at it, okay. So there is a famous story of a famous shoe company sending the salesman to a country where people long back people were not wearing the shoes or any footwear. So this marketing person was sent to that country. So naturally he went around and his eyes were on the feet of the people, and he wired back. That time there is no internet and the mobile phone. So he wired back, he sent a telegram saying that I am coming back, the people here doesn't wear any footwear, okay. So he went back. After few kind of month another marketing bright young man came as a marketing person. He was sent to the same country, okay. So he went around looking at the feet of the people. He wired back, you send 2 shipload of footwear because the people here don't wear footwear, okay. So people not having the footwear could be bad news for somebody and a good news for someone. So it's a way you look at it. So the same situation here in our Millet-Moore output, the fact that the Millet output when in the presence of asynchronous input can produce glitch is a bad news, but it's a good news. It means that when the input is synchronous you can generate the Millet output. That's what we should learn positively from this. Suppose if this start is coming synchronous would mean that in constant phase relation to this clock, okay. That means somehow this is generated indirectly from this clock, so that every time it comes with a specific delay with respect to this clock edge. It need not be that it comes every time with a very near to the clock edge, it can come every time with a fixed phase relation to the clock, okay. That's a synchronous. So when the input is synchronous there is no timing issue and the output can be the Millet output. So that's a game, that's a good kind of input. So I am putting that in the picture. So you have 2 synchronous subsystem. So you can imagine this is a register which is kind of the control signal is given by the state machine, maybe an enable signal, or this is a counter which is kind of enabled by the state machine. We have seen that, or a load signal of the state machine, the counter goes from the state machine, and the state machine and all these synchronous subsystems are working on the same clock. So and you see that there is some output, we don't know what kind of output, maybe if it's a counter, it's a timer, it's a decoded output which is going to the state machine input and so on, and let it be anything, but it doesn't matter. So this output is synchronous to this clock and that goes to the state machine. So state machine in this case has 2 output I1, I2. It has 2 control output which is O1, O2. Now it is very clear that O1 can be generated as a function of I1 and or I2, okay, as a melee output. O2 can be a melee output as a function of I1 and or I2, okay. It need not be that the O1 is generated only as a function of I1. O1 can be a function of I2 or I1, or there is yet another input which is synchronous to this clock. It does not matter, maybe it is coming from the outside world, somebody has synchronized to this clock and that can be coming to the input of the state machine. Then this O1 can be generated as a function of I3 which is synchronous with the clock. So that is a good news, that whenever you see a kind of the synchronous inputs, you can happily generate the melee output as a function of that if it makes sense. It is not that you struggle hard. If it is nice, if it works out, if it is part of the spec, then you can do that, and that give you all advantage of all these advantage. It comes, the output comes early to Moore output, number of states are less. Yeah, the glitch does not come since it is synchronous. So that is all about the melee output. When we come to a case study, I will show definitely 100% how the melee output can make the life easy. Only thing is that you should kind of from the day one when you practice, you should try and think whether the particular output can be melee output. That is my advice to you. So that is about the melee output. Let us move forward, okay. Now let us consider the little issue with the state machine generating the control signal. We have looked at it, particularly we have seen an example. In this case we have taken a register in our CPU example. I hope you remember this was the beginning of the course. We have we were looking at the advanced digital design and we have taken the CPU as an example. We have looked at the top down design. I have illustrated all the process, all the methodology by taking this example, okay. So there we had the CPU registers, and it is an 8-bit register, and we said that input is connected to the register, the Q output is connected to the same data bus because there is only a single internal data bus, and that was connected to the bus using a tri-state gate. So the game was that when some data from the input has to be latched to A, the state machine will give a signal, latch signal or an enable signal. In this case we call it RA_L, and that comes here. When this is high and the clock comes, the data was whatever was here gets latched, okay. And we mentioned that it is not that this latch signal is going as a clock, because it is possible that we want to kind of continuously load the data in some application, okay, not maybe with the CPU register. In that case it is very convenient, keep this latch signal or enable signal high for say 10 clock cycles. So continuously each clock the data gets latched, maybe this is a FIFO or a counter which is getting incremented, whatever, but may not make sense for the CPU register, okay. And we have seen we were looking at what kind of how the design should be to make that happen. That means when the latch signal is high and the clock comes, the data gets latched. So that is what is shown here. We have a state machine and some register or counter or some sequential kind of element which is working with the same clock, and the state machine is giving an enable signal here so that the input gets latched in this register, okay. So and we have seen one possible kind of implementation, very naive, the very first thing which comes to mind, because we say that when the latch is high and the clock edge comes, the data should get latched, okay. So this shows 8 flip flops, input and output are combined through a tri-state gate because there is only single data bus, and this is the enable signal, and we have just combined, okay. Now at the time of discussing this we did not look at the timing, okay, because we did not learn enough about the state machine. Now since we have learned, we can look at the timing. Now assume that this is coming from a state machine. So the pulse is like that, but then we know that the relation of this pulse to the clock of the state machine. So I am putting the clock frequency, the clock waveform. So we know that the state machine, something happened to the state machine, it changes a state and the output is decoded. So there is the output kind of come delayed with respect to the positive clock edge. So there is a TCQ, the state flip flop delay, and TOL, output logic delay, and it comes here. Okay. Now you can already see the trouble that we are ANDing here. So you AND this, you see there is an overlap 1 1 here and there is an overlap 1 1 here. Because of this AND gate delay, it comes delayed, and so you something like that, you get 2 positive clock edge and you see the trouble. Okay. We are expecting it to be clocked by 1 and it gets clocked by 2. Okay. Clocked twice, and in the case of register you may ask what is wrong with it, because say some data is here, you clock it latch here, you clock it again, it may latch here. Okay. But look at the timing, when this data may be coming from some other register in the as usual in the data path and through some combination circuit. So that means that is also clocked by the same clock. So data is kind of coming out of that register, and normally you know that we should be latching it at this edge. It is too early for, like, we have a clock edge here, but maybe that is too early because we decide the clock period depending on the TCQ, TCOMB and T setup, and we accommodate that in a clock period. So but here if you see the timing available from the clock edge to this clock is only little. So it's too early for registering. Maybe this is right, like we have decided that the data appears here, but then you know that the data gets latched here, but we don't know whether the data will remain there because that register is clocked by this, already the output is changing. Maybe this is coming in the whole time, after the whole time window and so on, then a wrong data can get latched. Suppose this is a counter which is getting incremented on this kind of latch signal, then you know that an edge comes, it gets incremented, probably again it gets incremented and so on. So this is because of this glitch. This scheme is not timing wise very kind of neat. Okay. So that is why I have discussed these points, that is why we have looked at this scheme. Okay. When we discuss the CPU, I have shown this scheme, and this does not have the timing disadvantage. Okay. So here we are not doing anything with the clock path, we are combining the latch signal in the data path. It has advantage in 2 ways. One is you look that when the latch is 1, the input is going there. Okay. So input gets latched, and you see that we know that because of the state machine decoding it comes delayed and it is made 1, and the input is coming from some register clocked by the same clock. So it starts appearing here, and it has all the time till the next clock period, and upon the clock, this clock edge, the data gets latched here. So it's very clean. Okay. But the only problem as you see is that the clock is coming, every clock this is getting kind of clocked. Okay. So maybe the data we enable sometime and the data goes here, but all other time this same output is recirculated back to input and so on. So assume that, say in a case where the latch signal comes only once in an hour, but unnecessarily this whole thing gets keep on switched so many times. Suppose it is 1 gigahertz, for 1 hour nothing happens, but because of the switching, a lot of power is getting dissipated. So the recirculating buffer is timing wise is very kind of nice, very clean, but the power dissipation wise it is really hopeless, absolutely hopeless. It has no relation to when the latch signal is high. All the time it dissipates power. It just a matter of frequency. Whatever is the frequency, it gets switched and the power is dissipated. Now so it means that for the power, as far as the power dissipation is concerned, the earlier scheme was nice, because when the latch signal come you get 2 pulses. Okay, you may be clocked twice, but if there is a 1 hour delay, nothing happens to the clock and there is no power dissipation. So let us probably, if you want low power dissipation, so when you design you can adopt this scheme, and we have seen that I will show examples, but you are into the like low power domain where you are working with handheld devices, mobile devices, then you need to dissipate less power, anything battery operated, or even now it's voice. There are even in a desktop PC there are millions and millions of PCs all around the world. Even slightest power saving will kind of help to reduce the overall power consumption of the world. So we should always look to reduce the power dissipation. So here see the game, the trouble comes because like we need actually our kind of clocking should happen at this edge, because when a latch signal comes here, the right time to clock is the second edge, because the data has changed at this clock edge and it has to propagate and come here. So the right thing to do is that we would like a pulse like this, okay, definitely, but the problem is that because it is coming half into this clock period, it's problematic. Suppose this kind of this latch signal, instead of coming with respect to the positive edge, assume that it is coming with respect to the negative edge. So this pulse will come start like this and stop like this, and if you AND it, then you get one pulse very cleanly here, okay. So that is the trick, okay. So if we can resynchronize this latch signal with a negative clock edge, okay, then it comes like this, and you can AND it with the resynchronized latch signal. The clock is ANDed with the resynchronized latch signal, then you will get a pulse correctly like this, and you can use it to clock this particular thing. So I have explained what's the idea behind, so that is what I am going to show now. So maybe I will show that and come back, okay. So this is what is we were discussing. So what we will do is that we will resynchronize this with the negative edge. It comes here, then AND it, okay. So let us look at that, so that is what is shown here. So you have the latch signal which is coming from the state machine. Now we put a flip flop, and there is a clock which is coming, and it's a negative edge triggered flip flop, okay. You see that there is a bubble, and so that means this latch signal is resynchronized to the negative edge. So that is we are calling clock 1, and that is ANDed with the original clock, and which generates a clock 2, which is used for clocking, okay. So let us put the waveform. So you have a clock, and normally the latch signal comes like that, and then we are looking at the clock 1 here, because it is going to a negative edge triggered flip flop. So it is, see, when the negative edge comes, this is 1, so the clock 1 output is 1, and when the negative edge comes, this is 0, so it becomes 0. So you get a pulse with a delay with respect to the negative clock edge, and you AND now this clock 1 with the clock. So this clock 1 and clock is ANDed, and you get a clock 2 with a delay, little delay, and now you are correctly, something is happening before at this edge, and we are supposed to hit this edge, and that is kind of latch with this particular clock edge. and everything works smoothly and there is only one pulse, this is clocked and it doesn't continuously dissipate power. So when you need to kind of you need a low power the clock gating, then one should adopt this scheme, and very standard scheme. Now earlier we had this scheme and this is converted to this. So what many a times the tools do is that when they see such a clock gating, they can easily convert automatically to this by inserting a kind of negative edge triggered flip flop. So many a times tools try to automate this kind of thing. Looking at this scenario, it converts into this. Even it is possible that you implement with a recirculating buffer and the tools detect that it is a clock gate kind of recirculating buffer, and it can do the proper clock gating by taking this resynchronize with the it can just replace that with this because it's very regular, and that is kind of very close to the, it has to be very close to the real flip flop, okay. Otherwise there will be timing issues because you are playing, you are introducing the skew in the path of the clock. So this is many a times done automatically by the tool. You give either this or this, then that can be kind of detected as a case for proper clock gating, and that can be introduced, and the FPGAs can be built with kind of resynchronizing flip flop near to a register and so on. It depends on the FPGA. So when we will look at the FPGA architecture, then we will see is there a scope, is there a flip flop nearby, another flip flop, so that this kind of game can be played. But mind you, there is one thing I should be mentioning here. So it looks that sometime it appears that it is enough to avoid this glitch problem if you kind of push this gate signal the enable signal here by introducing certain delay. You introduce suppose you can introduce 7 nanosecond and it appears here. So you might think that you can add a kind of 2 inverters to get that delay, but then you know that this delay depends on the clock period, and if you add arbitrary delays and change the clock frequency, it doesn't work. And you know that the delays are function of the temperature and the supply voltage and so on. So if you kind of in the slowest path you introduce a delay, and when it becomes fast this may not work and so on. So that's why we resynchronize with the negative clock edge, that you should keep in mind. So you should not try to kind of delay this and kind of gate it, that doesn't work because of the reasons mentioned. And now this is what we have seen. So this at least we said that this solves the problem of kind of the power dissipation, but many a times we use the same technique to achieve not only one, in this case it's just a latch signal, but there could be any number of kind of control signal in the data path, and that we have seen in the case of a counter. It's not that just one control signal, this is just like an enable signal for a register, but assume this is a counter. This could be an enable signal from the state machine, there could be a load signal from the state machine, there could be an up down signal from the state machine and so on. So this scheme can be kind of extended, we have already seen it, but I just maybe it's a right point to stress it again. So you can have any number of control signal, you can have different data paths like parallel data, shifted data, and when you have multiple control signal you need to have some priority, like if both come together which takes precedence, okay, that should be kind of decided, and that's very natural. We have seen that a control signal which comes close to the D will have the precedence. So let us look at this, let us look at this example, we have already seen it. So this is a counter with an enable, okay, very useful kind of structure. So the clock, suppose is a say 4-bit counter, then you have 4 flip flops, the clock is common, reset is common, and suppose a state machine has an enable, it is at the reset at the beginning. So whenever it is enabled it is incremented, that is a basic idea. So some event happens, the state machine enables it and it gets incremented, that is a game. So how it is implemented, you have a 2 to 1 mux, the enable is the select line of the mux, when the enable is 1 q is nothing but q plus 1, an incrementer is in the path, and otherwise the q is recirculated. So definitely there is participation, but the timing wise it is very neat, and we know how to write a VHDL code for it. So we write a process because we know that a single process will work for the registers preceded by some combination circuit, and this is what is a combination circuit. So we say we write a process with clock and reset in the sensitivity list, and we say begin if reset is 1 because it has a priority asynchronous, if reset is 1 then q gets other 0, else if clock even clock is equal to 1, and this is synchronous, we say if enable is 1 q gets q plus 1, end if, that means else you recirculate it, and end the end if of the first if and end process. So that is what shown here, process clock reset begin, if reset is 1 then q is other 0, else if clock even clock is equal to 1, and under that because there is a control signal, if enable is 1 then q gets q plus 1, end if, okay, that means recirculate, if not q is q, that is the meaning of it. So that is a 2 to 1 mux which is synchronous, which is coming to the input of the input D of the registers. So let us take another example where there are not one control signal, 2 control signal, we have already seen it but I am just reinforcing the concept. So here we have a load signal, a 2 to 1 mux, and when the load is 1 the input which is 4 bit gets latched here upon the clock, and if the load is 0 then if enable is 1, okay. So it has 2 control, load signal and the enable control. Enable is 1, the count gets incremented, otherwise count gets recirculated, and naturally we know that this has a priority because this comes first. So if irrespective of the enable, if load is 1 the input gets loaded, when the load is 0 then depending on the enable either it is incremented or the output is held, okay. And we know once again this register with this combination circuit can be coded as single flip flop, this is synchronous, so this comes in within the clock even clock is equal to 1. So same thing, process reset and clock begin, if reset is 1 q gets q, q is other 0, else if clock even clock is equal to 1, and the highest priority, if load is 1 q gets D in, else if enable is 1 q gets q plus 1, end if, okay, end process. So that is it, process clock reset begin, if reset is 1 then q gets other 0, else if clock even clock is equal to 1, if load is 1 then q gets D in, else if enable is 1 then q gets q plus 1, end if, that means else the q gets q, this is the end if for this is the end if for the main thing and the end process, okay. So that is what we have I think we have come to the last part of the lecture. So before taking up a new portion I would briefly tell what we have done. We have looked at the Mealy and Moore output, and we have seen that the Moore Mealy has an advantage, number of states are less, the output comes early, but there is a problem of glitch. So it works neatly with the synchronous kind of input, you can straight away go for Mealy output if it permits, and we have seen the control signal, and especially in the case of register a clock gating has timing issue because there are 2 pulses, and the solution is that to go for a recirculating buffer. It does not have any problem with regard to the timing, but all the time it is dissipating power, and this can be extended to the multiple control signal. We have seen a case of a counter with an enable, and where it works kind of without any timing issue, and we have seen the VHDL code, and when we have also seen a counter with load and enable, with which load has a priority, and once again it can be coded in a single process, and we have seen the example, we have seen it earlier, and we have also seen a kind of low power solution of clock gating. To avoid this kind of glitches, we resynchronize this latch signal with this negative edge, and adding a constant delay won't work because the clock period can change and the delay of the combination circuit itself can change. So we resynchronize with the negative clock edge, and the resynchronized version of the control signal is gated with the clock, and that works as a clock. So this works very neatly. There is no issue with the timing. Only thing is that it uses an additional flip flop for a set of registers, not that it is there could be 16 kind of flip flops and one additional flip flop is required depending on per control signal. We can say we require an additional flip flop for each control signal to resynchronize. That is a basic idea of clock gating for low power. So today what we have seen is that we have completed the Mealy and Moore output, and we have seen the advantage where the Mealy can be safely used, and we have looked at the clock gating solution, recirculating buffer, what is the issue, timing issue with the clock gating, and how it is avoided in recirculating buffer. But the issue is that the power dissipation, and we have seen a clock gating scheme for the low power, and we have seen the extension of kind of recirculating buffer for multiple control signal where there is priority, how to design it, how to code it, and all that. So in the next lecture we will try to take some more issues, such timing issues and other issues of the state machine. Then I am hoping either take the VHDL coding of the state machine, or we probably start looking at the PLDs. So that is a plan. So today I am winding up. I advise you to go back because we have covered quite a lot. Go back and review, learn well. I wish you all the best and thank you.